Hello, everyone. So this is just a short PowerPoint on kinematics in one dimension. This will be a series of videos. This is the first one. And then I have another one prepared for kinematics in two dimensions. And a third video with some advanced problems. But this is just a review of the basic concepts in kinematics in one dimension. And of course, we know very well that when we talk about one dimension, it can either be horizontal, the motion of the object could either be on the horizontal or the vertical. And how important that we know the different equations that we are using in problem solving. So let me just so this PowerPoint focuses on the equations and how they are applied. It will guide you on how to solve basic problems in 1D or one dimension. So kinematic equations are used to describe one-dimensional motion along the x-axis or the y-axis with constant acceleration. Of course, it was already discussed before that motion of the object can be vertical and that falls under free fall. Each equation shows a different relationship among physical quantities like initial velocity, final velocity, acceleration, time, and position. So these four quantities are found on the different equations that may be applied in one situation or one problem. And these are those equations. Basically, all your problems will be guided by the following equations. It's easier to solve or to analyze a certain kinematics 1D problem by checking first the given, see what values are already available in the different equations, and then choose the equation that gives you the least number of unknown. Okay, so these are the four equations. These are the guiding equations for kinematics. The first one is final velocity. Excuse me. You might find other subscripts or notations in other references. For the rest of the problems, I will be using the following. So this is final velocity equals initial velocity plus AT or acceleration times time. We also have a formula for average velocity. That's just, of course, taking the average of the two quantities, initial and final velocity. In terms of displacement or distance, we can use this formula x sub f equals x sub I plus vit plus 1/2 at squared. And for final velocity, we have vf squared equals vi squared plus 2ax. You can already solve different kinematics related problems by just mastering the use of the following formulas. Always remember that A is positive or acceleration is positive if velocity is increasing. It means that the object is accelerating or moving faster. And A is negative if the velocity is decreasing, meaning that's deceleration or the object is actually slowing down. Okay, again, some suggestions. You can always illustrate the problem, get the given, and then look for an equation wherein there is the least minimum unknown possible. And then, of course, just go ahead and solve the problem. Okay. And these are problems that were taken from your activity one. You might be wondering where the problems are coming from. So I took first the 1D problems from activity one. So let's start. Okay, the first problem you saw there, you might have had seen different variations of the unknown. So what I did was compress those problems and just I came up with 5 unique problems from your activity one. Okay, the first one is a plane has a takeoff speed of 88.3 meters per second and requires 1365 meters to reach that speed. Find the acceleration of the plane and the time required to reach this speed. Okay. For some, you might have seen the solutions online, but you might not have seen a video solution beside providing these for you, so that at least you can get a grasp on how to be able to solve it. Just give me a moment. Okay, as I've said, it's just easy to use those formulas that we were just shown earlier. All we have to do is really get the given quantities already available in the problem. We can see a takeoff speed of 88.3 meters per second. We can say that, of course, the plane starts from rest. We can assume that initial velocity is 0. We can use that takeoff speed as final velocity. Why is that? Because it's like you can already gauge from the problem that it's the terminal velocity because we have a given displacement or distance, which is 1365. So we can say that this is our displacement, or the distance traveled by the plane. And it's looking for acceleration and time. So we can say that's the, we're looking for acceleration, and we're looking for time. We can go ahead and solve this problem right away by using one of the formulas. We have final velocity given. We also have x, so we can use the fourth or the vf squared equals vi squared plus 2ax formula. Why is that? We have a given final velocity. We have a given initial velocity. We're looking for a. We already have a given distance, so we can just get a by using, of course, that formula, rearranging it all over 2x. So let's continue that here. We substitute the values. That's 88.3 squared minus, of course, 0 squared all over 2 times 1365. And of course, just compute that. We get an acceleration which is 2.85 meters per second squared. So this is the first value to obtain, acceleration. Now, the second is looking for time. So we have to get time, and of course, we'll always use the basic or the simplest equation possible. So we can use our final velocity equals initial velocity plus AT formula. Why is that? This is 0. Thus, we can get time. Time is just final velocity over the computed acceleration. And this is 88.3 all over. This is, acceleration is from this one. You always assume that what you're getting is correct. Okay, let's get that. That's 2.85. And if we get that, this, we compute this, we get 30.98 seconds. Okay, so these are the two answers for the first problem. Again, straightforward solution, following the given formulas, looking for the equation that has the least number of unknown. These are your answers. Acceleration is 2.85 meters per second squared, and time is 30.98 seconds. Okay, let's go straight to the second problem. A person walks first at a constant speed of 5 meters per second along a straight line. We can say that if we have a person, we assume that that person walks, let's say this is point A to B initially. So B, A, B, that person is walking 5 meters per second. What is that? Just erase that. And then it says that the person goes back, B to A. So the third person, after reaching this point, would go back. And that is VBA 3 meters per second. That's just the given in the problem. It just says that the person walks along a straight line. Initially, let's assume that's point A to B at 5 meters per second and goes back, but at a slower pace, which is just 3 meters per second. So what are we looking for in the problem? What is her average speed over the entire trip? And what is her average velocity? We know very well the difference between average velocity and average speed. Speed is, of course, talking about distance over the change in time, whereas velocity talks about displacement over the change of time. And we have formulas for distance. Distance is simply, okay, let's just use S average. We know that when we're getting S average, we get the total distance, as I've said. That's the main difference, will be distance and displacement over total time. So we know that the total distance, we don't care about the direction. It will just be, of course, DAB plus DBA. Will be the distance from A to B plus B to A. And if we, of course, get the total time, that's simply TAB plus the time it takes to cover points B to A. However, it's also safe to assume that that distance is the same. It's just that the person going back walked slower, okay? So DAB is equal to DBA. We can just assume that it's D to make it more simplified, or just to simplify it. And then we can say that the DAB is actually D over VAB, and DBA is equal to D over VBA. Thus, we can already say that our formula will be D plus D, simplifying it. This is D over VAB plus D VBA. Of course, you can always compute them separately if you just don't like doing all the substitution in the formula. But I found this to be the easier way, or the better way, because it's very straightforward. So what do we do next? We just use that formula. Let me just pull up another sheet. Okay. Let's just have a new one. Okay, let's continue. Okay, we continue with S average equals. We just apply the formula now, D plus D all over D of course, VBA plus D VAB. Okay, all over. This is already a simplified version of the ones we had a while ago. VB times VBA. This is already coming from this one. I already simplified it. That's why I'm getting this already. Because if I add or get the sum of this, you have to get the LCD, which is VAB, VBA, and then simplify it. That's why I got this. Okay, sorry for the handwriting. So we simplified further. That's D plus D, that's 2D all over. We can already get the simplified version. So this is getting this. This is the denominator, putting it up, or getting the multiplying the reciprocal. That is VAB times VVA all over D times VAB plus VBA. Therefore, we can cancel B. So this is 2 VAB VBA all over VAB plus VBA. And then what we can do is just substitute or plug in the given. We have given velocities, A to B and B to A. Therefore, we can say that's 2 times 5 times 3 all over 5 plus 3. That's simply 30 over 8. So this is now equal to 3.75 meters per second. Okay, that will be the average speed. You just can't get, say, 3 plus 5 divided by 2. That would give you a wrong answer, because you have to consider that they might have the same distance, but the velocity for each given is different, because going back, the person had a slower speed. Okay. Okay, we'll just, there's also another required in the problem, which is what is her average velocity for the entire trip. This is sort of a common sense question, meaning, letter B, what is the average velocity? We know that average velocity is equal to the change in displacement over change in time. However, we're talking about displacement, and we know that that person walked from A to B, then B to A. Thus, we also know that if the person or the object goes back to its starting point, the displacement will become 0. So this is delta T. So the answer for the next one is 0. Okay, because the person went back to the starting point. Next, let's have the next problem. A ball is thrown upward from the ground with an initial speed of 25 meters per second. At the same instant, another ball is dropped from a building 50 meters high. How long will the balls be at the same height above the ground? Okay, this is a free fall problem, and it talks about two balls. One being dropped from the ground, to the ground, and another one being thrown up from the ground. Sorry for the prepositions. Okay, let's just illustrate it quickly. We have okay, sorry for that. So we have the height of our building. Okay, so the height here is 15 meters. Okay, says here. And then a ball is thrown upward from the ground. So we have a ball that is being thrown upward at a speed of 25 meters per second. And another ball is dropped. It's a different ball, okay? Let's assume that this is ball A and ball B, and this is thrown down from a certain, from 15 meters, and of course it goes down. We can say that they will meet. Let's assume that ball A will have a height once it's thrown upwards, and ball B will meet it somewhere between 15 minus h. Okay, so let's write those so that we can you can always refer to them after. So h will be for ball A. This is height of ball A, because we assume that when we throw it upward, it would reach a certain height. And B, being thrown downward, will already have a reference of 15 meters minus h. This is for ball B. So as I've said also during the first PowerPoint for this topic, that you can always convert the given formulas into vertical motion or for free fall. You can use them for free fall computations. So let's use this formula. Since we're talking about height, we can use, instead of x, let's use y. Okay, we have that. Some sign changes on the way just to signify direction. We see that downward is always negative when it comes to direction. We've already agreed on that. Right is positive, downward is negative, upward is positive, left is negative. But of course, gravity is another thing. When it's downward, when motion is downward, we have to use negative 1/2 gt squared. Okay, because the sign is, of course, negative. So, but this is the generic equation. So for the falling ball, let's first analyze the falling ball. We can say that its final height is negative 15 minus h. Ma'am, why negative? Because going down. The direction is going down. And then we know that if it's a falling ball, our frame of reference here will be 0, 0. And then this will also be 0t. Why? It starts from rest. It doesn't have an initial velocity. You throw it downward. Thus, its initial velocity is 0 minus 1/2 gt squared. Why negative? Because gravity going down, we will be using here negative just for direction. Therefore, we can simplify this equation. That's negative 15 plus h equals negative 1/2 gt squared. I'm using heights because they're more discretely seen in the problem. Okay, and we can say that this, let's just rearrange this. This is h equals 15 minus 1/2 gt squared. Let's say that this is equation 1. Okay, for the rising ball, I don't know how to call it actually, or just being the ball thrown upward. I'll call it rising. Anyway, so I think you get what I mean. For the rising ball, you can say that we can use the same formula, yf equals yi plus bit minus 1/2 gt squared. And we can just plug in the values. That's h equals, also this one is 0 as its frame of reference, but it has an initial velocity or initial speed of 25t minus 1/2 gt squared. Okay, then what do we do? we already equate equations 1 and 2. Okay, let's insert the slide again. Okay, now we'll just equate equations, equating equations 1 and 2. We can get in terms of height, because previously what we did was get h and then get h. So we will equate 1 and 2. We just can say that this is 15 minus 1/2 gt squared equals 25t minus 1/2 gt squared. And since both sides of the equation have this, we can cancel this. Thus, t now is equal to 15 over 25, and t here is 0.6 seconds. Okay, so that is how you solve the next problem we have for the activity. Okay, so let's go to the third one. These are all applications of the initial kinematics equations, both for horizontal and vertical. So the next one. Okay, this is the key problem, wherein a student throws a set of keys vertically upward to her sorority sister, who is in a window 4 meters above. The second student catches the keys 1.5 seconds later. With what initial velocity were the keys thrown, and what was the velocity of the keys just before they were caught? So we're looking for two quantities: initial velocity when the keys were thrown and the velocity of the keys just before they were caught. Of course, just before they were caught, because once they're caught, they stop, and that velocity will become 0. Simply put, if you want to illustrate that problem, we have a 4-meter height. We have somebody catching the keys here. We have somebody throwing the keys here. Okay, we're looking for the velocity here, the point before that girl catches the keys. And we're also looking for the initial velocity here. That will be the throwing velocity of the keys. Those keys are thrown vertically upward. And that whole catching will happen in 1.5 seconds. You may or may not illustrate the problem, but if it helps you by illustrating it prior solving it, then do so. Okay, let's get the given. Frame of reference, yi equals 0. We can also say that our final height will be 4 meters. The whole thing happened in 1.5 seconds. Okay, we can use A as your G. This time it's upward, therefore we can use 9.8 meters per second squared. Okay, the whole thing is going upward. So let's just use our formula again. So YF is equal to YI plus BIT plus 1/2 GT squared. We can extract or isolate BI. BI now is equal to YF minus YI minus 1/2 GT squared all over P. Substituting the values, we have BI equals 10.02 meters per second. Okay, let me just show you the values. That's 4 minus 0 minus 1/2 minus 9.8, 1.5 squared all over 1.5. Okay, so we get that velocity, which is 10.02 meters per second. Always round up to the nearest 2 decimal places. And we're also looking for the final velocity. just before they were caught. So you can just use the formula Vf is equal to Vi plus 80. So that's 10.02 plus negative 9.8 times 1.5. Therefore, your final velocity here is negative 4.68 meters per second. The negative signs just show direction. Okay. So this is your answer. Keep the negative sign. Okay. That's the third problem or the fourth problem already. I think that's the fourth. Okay. The next one will be the last problem for the activity for 1D. There's a separate video for 2D because they have different problems. I mean, different equations. Okay, the last one will be an inquisitive physics student and mountain climber climbs a 50-meter high cliff that overhangs a calm pool of water. Excuse me. He throws 2 stones vertically downward, 1 second apart, and observes that they cause a single splash. The first stone has an initial speed of 2 meters per second. So we are looking for 3 quantities here. How long after release for the first stone do the 2 stones hit the water? So we're looking for time. What initial velocity must the second stone have? The 2 stones are to hit the water simultaneously. And what is the speed of each stone at the instant the 2 stones hit the water? So we can always assume a frame of reference. You still want me to, okay, let's still draw it. So we have a 50-meter height. So this is, there are 2 stones being thrown. And it's A and B. So the first stone was thrown at time t, and of course this will become t plus 1 because the second stone was thrown a second later, and the initial velocity for A is 2 meters per second. So we can go straight ahead and use the solution for the equation we were using from the previous problem. We can say that YF is equal to YI plus VIT plus 1/2 AT squared. I'll have more examples on the third video. This is just for the activity because some of you requested it. So this is now directional. It's downwards. So again, that's negative. Just give me a moment. Okay. So we can say that it will be, since it's downward, that's negative 50 equals 0 minus 2t. Why 2? Why negative 2? I mean, because it's going down direction again. Plus 1/2 negative 9.8 and then t squared. And just rearranging that and using shift solve or whatever formula. You can use quadratic formula. You can use your shift solve. You can just input this directly to your equation tool in your calculator. You get time here for 3 seconds. Okay. And letter B, what initial velocity must the second stone have if the 2 stones are to hit the water simultaneously? When we know that for the time here, because the second stone will hit it at 2 seconds, because after 2 seconds, 3 seconds minus 1 second, because that's 2 seconds. Okay, this is for the second stone because this is t minus 1. So this is for the second stone. We can say that using the same formula, we just plug in the values. We get VI, or initial velocity, as negative 15.3 meters per second. We will still use this formula. Okay, but this time you are using t and your initial velocity is not 0. You have to use another value because you're looking for it. So initial velocity for the second stone is negative 15.3 meters per second. Yeah, I just saw the time. That's why I went a little faster. And finally, the third requirement will be the final velocity per stone. So for letter C, we're looking for VF. So for stone, we can just use the VF equals VI plus AT. We can use -2 plus -9.8 times the time, the catching there. This is -31.4 meters per second. And for the second stone, we can also use the same formula. VF is equal to VI plus 80. And that is -15.3 plus -9.8 times 2 this time, because after 1 second. So final velocity of the second stone is -34.8 meters per second. So this is how you solve the first set of problems in your activity. I'll be uploading solutions of the next set because they are falling into the category 2D. Those are projectile problems, okay? And for now, that will be it. Thank you so much. Please don't forget to subscribe to my channel if you have time. Thank you so much and good day. Thank you.